So we'll discuss regarding the second classification of second order. P.D.E. So consider the second order semi-linear equation as we have discussed in the previous lecture. That is, consider the following second order semi-linear P.D.E. That is L of u plus g of x, y, u, ux, ui equal to 0, where L is an operator which is apply on u, which is r of xy del square by del x square, s of xy del square by del x del y plus t of xy del square by del y square, with this r square plus s square plus t square is not equal to 0. That means all these three r, s and t are not simultaneously 0. And this r, s and t are continuous function of x and y. So they are continuous function of x and y. We further assume that this function possesses the continuous partial derivatives with respect to x and y. So further, we assume that these functions, that is r, s and t that we are talking about, possess the continuous partial derivatives. With respect to x and y. Now what we'll do, we'll change the variable here to xi and eta. And now the calculation is very lengthy. I cannot say complicated, but it is lengthy. We change the variable and these variables are independent variables, x and y, to xi and eta. Where xi is a function of x and y and eta is also a function of x and y. We assume that the gradient of xi eta with respect to xy is non-zero. That means xi x eta y minus xi y eta x is non-zero. Why we are assuming this? So that the transformation is invertible at least locally. That means in some neighborhood, this transformation that we are transforming from xy to xi eta will be invertible transformation. So that's why we are assuming this condition, and it is important. So that's why we can able to construct or convert the equation into that form. Now it is easy to see that we note that what will be the ux. Now what is the situation? U is a function of xi and eta and xi and eta are the function of x and y. So if you want to calculate the partial derivative of u with respect to x, you have to go with the three path. So that will gives me del u by del xi into del xi by del u. So that I am writing as u xi into xi x plus u eta into eta x. Have you understood this? Similar manner it is uy. U xi xi y plus u eta into eta y. Ultimately, I want to establish everything which we have here, that is del square u by del x square, del square u by del x del y, del square u by del y square. That we are trying to find out here. So that's why it is u x y. That means a differentiation of ux with respect to y. So here we have again a same situation. Ux is a function of xi and eta, and xi and eta are the function of x and y. So that's why this will gives me here the product rule will apply, because u xi and xi x, both of them are the function of y. Okay, so here the product rule will apply. So we'll have, it is del by del y of u xi x as it is, plus u xi as it is del by del y of xi x. Plus here is also the product rule will apply. You will have del by del y of u eta into eta x as it is, plus u eta as it is del by del y of eta x you will have. Now, as I told you, this u xi is a function of xi and eta are the function of x and y. We can apply this rule here, that is a chain rule for partial derivative, will gives you u xi, because first it is a derivative with respect to xi and then u xi derivative with respect to x. So that's why it is u xi x plus u xi eta x, and all this thing will multiply with xi x that we have already here, plus this quantity, that is u xi xy we can write. Here again we can apply this chain rule. So we'll have, it is u eta xi x plus u eta x, and all this quantity will multiply with eta x, plus here it is u eta xy. So finally what we get, sorry, we are differentiating this with respect to y. So here it should be y, where we have written x. This should be y. So here it is y, here you have y, here you have y, and here also you have y. Here is also, instead of x you will have y. So here you have y. This is sorry. Let me do it again, because I made a mistake here, very big mistake. Let us do it again. So here we are differentiating this ux with respect to y, not x. That was my mistake. Actually, we are differentiating with respect to x. So it is del by del y of uzi into xi x as it is, plus xi u xi as it is, del by del y of xi x, plus the product will apply here. It is del by del y of u eta into eta x plus u eta del by del y of eta x. Now here if I use this one, here it is u xi. So u xi is a function of xi and eta are the function of x, y. So and y it is at these two places. So you have two path here, that is u xi uy plus u xi eta y, and this should multiply with xi x plus u xi. This I can write down xi xy. This one plus this quantity, again applying the same rule, it is u eta xi y plus u eta that is eta y plus eta x into eta x plus u eta into eta xy. And if you simplify this, that means this xi x will multiply to this quantity, we will have this u xy will be u xi x xi y, that you can observe xi x xi y. Then you will have u xi eta xi x eta y plus u xi eta xi x eta y plus u xi xy as it is, that is this value as it is. Now if you multiply this, you will have, it is u eta eta x eta y plus u eta x eta y. That is this eta x will multiply to here, and the last quantity is u eta xy. So this quantity is will have, it is u xy. Now we'll calculate what is u xx in the similar manner as we have discussed here. That means del by del y, instead of y we have x. That means we are differentiating with respect to x. We'll have del by del x of u eta into eta x. That is the product rule will apply here, and plus u eta as it is, del by del x of eta x plus del by del x of eta xi into xi x plus eta xi as it is, del by del x of not x but it is u eta. I have written here, it is u eta into eta x. That is, we are differentiating this quantity with respect to x plus u eta as it is, del by del x of eta x. Now as we apply the same rule, we can do it here. That means you have u xi into xi x plus u xi eta into eta x. This will multiply with xi x plus u xi, this will be u xi xx plus this will be gives you u eta xi x plus u eta eta x plus u eta into this is eta xx. So therefore what we get, it is uxx will be u xi into xi x square plus u xi eta xi x eta x plus u xi xx. That you can observe the things we got. Here you will have u xi eta xi x into eta x. So it is plus u eta xi x eta x plus u eta x square plus u eta into eta xx. Similarly, now I will not do the calculation for uyy. Hope that you will be able to do it, that calculation yourself. What you will have here, it is xi. Whenever x is there, we have just y. So replace this equation with y because it is symmetricity is there. So it is xi y square plus u theta y xi y eta y plus u xi y plus u eta xi y eta y plus u eta y square plus u eta yy. So this is the quantity we'll get for uxx, uyy and uxy. So therefore, if I can now simplify ruxx plus suxy plus tuyy, will substitute all this value here. Uxx is this value, uyy and uxy will substitute here. What will be the coefficient of u xi we got here? Just see u xi. So u xi, it is coming into all the three equations, here also, and here also. So as per this, uxx is multiplied with r. So u xi with r into this xi square x, xi x square. So it is r xi x square plus s, that is uxy. Uxy has xi xi is this value, xi x xi y. So that's why it is plus xi x xi y plus t xi y square. This is the coefficient of uxx. Then the coefficient of u xi eta. U xi eta and u eta xi is the same value. So that's why we have here, we have two terms of that, this term and this term, and it will coming two times. You can see that because u xi eta is same as u eta xi. So these two values are same. So that's why it will coming two times. So it is 2 times r xi x eta x plus s, that is in r here. This is also coming 2 times because it, and this term is not common term. That's why it is s plus s into xi x eta y plus eta x xi y plus 2 times t, because in the uyy also we have coming 2 times here and here. Due to this, it will come 2 times. So it is 2 times t xi y eta y So this is the coefficient of u xi eta. Now u eta eta will have r, that is u eta eta, you can observe that is this quantity here. It is r into n x square, that is eta n, eta x square, plus 2 times or s eta x eta y, that is this quantity. And here you will have this quantity, that is plus t eta y square, plus you will have some function of plus some rest of the quantity which is left, which is from here, that is this plus this plus this, and this plus this. All this quantity, I can say it is some function plus some function of xi eta, u xi, u eta, and u. So it will be some function of this quantity. So what we can say, the equation, the original equation, this equation, I can say equation number 1. Now this equation 1 will change to another equation because we have transformed all the variables, that is xy variables, to xi and eta variable. So we'll write that. Therefore, the equation 1 becomes, by substituting this value, we'll have it as, I can say it is a of xi x xi y u xi xi plus 2 times beta into xi x xi y eta x eta y u xi eta plus c times, sorry, a of eta x eta y u eta eta equal to some function g of xi eta u xi and u eta. I will call this as equation number 2, where what will be the value of a and b we have, where the value of u v, that means instead of u v here. So here what will be the value of this a, that is a coefficient of u xi xi we have here written, that is this, that is u r u square plus s u v plus t v. And you can also observe that this quantity and this quantity is same by just replacing xi x by eta x and xi y by eta y. So that is exactly a of uv is u square plus, sorry, r u square plus s uv plus t v square. And what will be the value of beta uv? It is not actually beta uv, it will be a 4 function. So that's why it is beta, I can say u1 v1 u2 v2. So as per this, you just observe that that is the middle portion that we have here, that is 2r. The 2 is already calculated, so it is, because here I have already used the 2 here, so we will not use that 2 here. That is r u1 u2 plus 1 by 2 s 1 by 2 into s u1 v2 plus u2 v1 plus t into v1 v2. We'll call it, this is the equation 3 and this one is equation 4. Now very interesting situation is occur here. If once we convert our differential equation into this form, then it is easy to classify our differential equation. So Here I am giving you one exercise to prove, and it is very easy to do, so that it is a of xi x, xi y, eta x, eta y minus beta b square xi x, xi y, eta x, eta y. That means this quantity is nothing but the 4 times RT minus S square upon 4. So here it is 4 RT minus S square upon 4 into xi x eta y minus xi y eta x square. So this quantity you will have, and it is just a simplification. You have to do it here by substituting this a. The value of a is this r u square plus s uv plus t v square, and value of b is this. You have to substitute this value on the, you start with the left hand side and try to prove the right hand side is there, and with this very easy to deal with. We'll call it this as equation number 5. It's required, it's most important situation will appear here. Now the problem is to choose the xi and eta so that this equation number 2 will take a simpler form. So that is our objective, to classify. That means the problem now is to choose xi and eta so that the equation 2 takes a simple form. In that, the case number 1, where the r square minus 4rt, which we have obtained here, s square minus 4rt, that is this situation we can talking about, is positive, then we shall show that xi and eta can be chosen that the coefficient of u xi and u eta in 2 vanishes. That means whenever s square minus 4rt is positive, we'll choose our value of xi and eta in such a way that in the equation 2, that is this, where this value, I can say this value will be 0 and this value will be 0. So only the equation will contain in the form of u xi eta. And how we can do that? That is the procedure. So for that, let us consider this. Consider r alpha square plus s alpha plus t equal to 0. Now this is a quadratic equation in terms of alpha. So obviously this equation has 2 roots. Okay. This equation has 2 roots, but we have s square minus 4 rt is positive. That is our condition we have taken. So that's why this polynomial or quadratic polynomial has two real roots. In fact, two distinct real roots we have. So what we can say, therefore, this equation has two distinct real roots. Let us say that roots are lambda 1, which is a function of xy, and lambda 2, which is also a function of xy. So that two roots will assume lambda 1 and lambda 2. If once we choose this, means once we find out this value of lambda 1, lambda 2, now we'll choose xi and eta such that, so how to find out the value of xi and eta? So that is the equation. Del xi by del x is equal to lambda 1 del xi by del y and del eta by del x is equal to lambda 2 del eta by del y. This is the two first order linear differential equation in terms of xi and eta you will have. And so it will have a solution. This are first order partial differential equation. For xi and eta. If it has a solution, let's say f1 xy is equal to c1 and f2 xy is equal to c2 are the solution of the ordinary differential equation, that is dy by dx is equal plus lambda 1 of xy equal to 0 and dy by dx plus lambda 2 of xy equal to 0 respectively. Then what we will have, it is xi equal to, you can choose f1 of xy and eta is equal to f2 of xy. Whatever the solution for this one, will consider as the value of xi and eta, will be a suitable choice. And this choice of xi and eta will leads to a, and the value of a, which we have already talked in this equation, will be 0. So this choice of xi and eta makes a of xi x, xi y and a of eta x, eta y is 0. And from the equation number this, that is equation number 5, which we can say that the b square will be positive, because this value here we have assumed that s square minus 4rt is positive. That means 4rt minus s square is negative. This side, this, if this a is 0, this value is 0, then this is negative. So that, and this is already positive. So that means b square is always positive. Hence the equation is reduced to So I can say that from equation 5, in this case, we'll have b square is positive, strictly positive. That means b is non-zero. Hence, the equation 2 reduce to del square u by del xi del eta equal to some function of phi xi eta u eta xi u eta, where xi and eta are called the characteristic curves of equation number 1. That means they are the characteristic curves, and in this case the equation will reduce to this situation. In that case, we will say that the equation is hyperbolic type and the example is a wave equation. Okay. So what we can say, the curve xi of xy is equal to constant and eta of xy equal to constant are called characteristic curves of equation 1. The original equation 1 is there. Now case number 2. In case 2, let's say s square minus 4rt equal to 0. Let us say this situation we have. In this case, that the polynomial that is r alpha square plus s alpha plus t equal to 0. So in this case, this polynomial, that is s square minus 4rt, that is b square minus 4rt is 0, b square minus 4ac is 0 here. If it is there, then we'll have two equal roots. The polynomial has two equal real roots. Okay, so in that case, let us define xi equal to f of xy, where f of xy is c1, is a solution of dy by dx plus lambda xy equal to 0. So dy by dx plus lambda xy equal to 0 is the solution. Now let us take eta as any arbitrary function of x and y, because one solution we got from this, so we need to looking at another function. So that is eta will take any arbitrary function, whatever you want, which should be independent of xi, independent of xi, and from equation 4 again we just observe, that means r square minus 4 beta is 0, so this side will be 0, and will have a is also 0 due to this r square minus 4rt is 0, so this value of a is also 0, so we'll have value of b is 0 in this case. So from 4 we can say that B is 0, since A of xi x xi y is 0. The value of A is 0. And since this eta is independent of xi, A of eta x eta y will be non-zero. And therefore the equation 2 that we have here, since this beta is 0, the equation 2 and A of xi x xi y is 0, so only the equation will reduce to this quantity, that is u xi eta eta equal to some function of the things you will have. So in that case you will have, therefore the equation 2 reduced to del square u by del eta square equal to some function phi of xi eta u xi x u eta 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 u xi, sorry, u eta and eta xi. So it will be a function of this. Now case number 3, that means s square minus 4rt is negative. So if it is negative, obviously that equation will have two complex roots, that is r square, that equation that we can have, this equation r alpha square plus s alpha plus t equal to 0 has two complex roots, and therefore there is no characteristic curves in this case is possible. So we'll say that this is formally the same case as 1. However, here the roots are complex. So we have a complex roots here. Proceeding as in case 1, we find that equation 2, so whatever we have did in the case number 1, that means we have considered dy by dx is equal to lambda, but in this case lambda will not be a real roots, it will be a complex roots. Okay, so therefore we have some situation which is, if you can proceed in that manner, our equation will reduce to this one, it is del square u by del xi del eta. But this will consider the two form, this will form a two things, that is a real factor is there and a complex conjugate will be there, and xi and eta are the complex conjugate of each other. So you will have no real characteristic curve in this case is possible. So if you want to do that, we need to assume the value of xi and eta. So it is proceeding, we find the from equation 2 the reduced to the form del square u by del xi del eta equal to some function phi. But that the variable xi and eta are not real. They are not real. In fact, they are complex conjugate of each other, because the roots are always in complex conjugate. Therefore, there are no real characteristic curves in this case. So there is no characteristic curves is possible. We make the further transformation. That means we need to substitute the value of alpha as 1 by 2 xi plus eta. That will be a real part of this, and beta is equal to I by 2 eta minus xi. That is a complex part of it. And then in this situation, if we assume this alpha and beta, then the equation 2 reduce to del square u by del alpha square plus del square u by del beta square equal to some function of alpha beta u alpha u beta. And in this case, it is of the type elliptical type, and the example is Laplace equation. So whatever we have discussed till now, that is classified here. It is saying like this: the first one, as a square minus 4RT is greater than 0, then this equation is known as hyperbolic type. This is very important in the NET examination. Many a times this type of questions they were asked. So I am talking about the equation which is of the form R u xx plus s u xy plus t u yy plus some function of x y u ux uy equal to 0. So if your differential equation, second order differential equation, is of this type, and if you found that r square minus 4rt is positive, then such differential equation is known as hyperbolic equation, and the example is a wave equation for that. Second one is r square minus 4rt is equal to 0, then it is called a parabolic type. And the example of a parabolic type is a heat equation that we have talked. And the third one, that is r square minus 4rt is negative, which is elliptic type, which is Laplace equation. So this equation it is of this type, that is hyperbolic type, parabolic type, and elliptical type. So in this first case, that is into the first case, the canonical form will be reduced to del square u by del xi del eta equal to phi of xi eta u xi u eta. So that is the first case. That means if it is hyperbolic type, its canonical form is this. The second one, that is if it is a parabolic type, that is the second one. When it is the second one, then the canonical form, it is of this form, del square u by del eta square is equal to phi of xi eta u xi u eta. So it is of this form. And the third one, that means it is of elliptic type. That means it is this situation is there. Then you will have the canonical form, which is del square u by del alpha square plus del square u by del beta square is some function of phi, where function is alpha beta u alpha u beta. So this is the classification of second order partial differential equation is there. We'll discuss the example based on this classification into the previous lecture. Into the next lecture. So we'll stop here. If you have any questions till now, you can ask.